everybody. I'm Sujo Bose. I work at Sabre Holdings in the big data team. We work on both the Hadoop environments as well as looking at the online side of big data, which is the NoSQL part. So I'm going to talk about an efficient method of processing large XML, large and complex XML in Hadoop. So this will be the outline. Let me just mention what the problem is, and then talk about a little bit about the schema on read versus schema on write. And we'll mention about the Avro format, which seems like a good candidate to represent XML data and how they map between each other. And we'll look at the performance and storage consideration and some other alternatives. So hopefully in this session you'll learn about three things. One is how to store and process large and complex XML data and the interfaces that are available that can help us access that data through standard interfaces like Java MapReduce, Pig, or Hive. And we'll look at some variations of those methods with their trade-offs. So as we all know, XML had been prevalent, especially once the web services and SOA started. And a lot of communication happened via XML, and it's a preferred format for storage at that time until newer formats came in. So a lot of these logs and machine-generated data is in XML. So I believe a lot of organizations will be having a lot of XML data to deal with, from which they can gather insights. XML is very good. It is very flexible. It has metadata baked into the data. But along with that comes the complexity in terms of arbitrary nesting that can be done that makes the data types a little bit complex. And also, as we can see, that parsing takes CPU time, CPU resources, and memory as well. Combine that with volumes of data in a big data system, then we have a big problem. So challenges, as I said, it's resource intensive to parse the XML. And then once the XML is parsed, then obviously the rest of the analysis can be done. So once we have to do this repeated queries more often, then a lot of time is being spent in parsing. So we'll see some of the performance comparisons that we have done to look at what time is spent in XML parsing versus if we had stored it in a pre-parsed format, then what the benefit in terms of both storage as well as processing. So traditionally, Hadoop is more of a load as is and then do transformation on the fly on a query. So it's more of a schema on read versus schema on write. Now that is good in most cases, but as we can see, once we deal with semi-structured data, especially XML, that doing some amount of ETL rather, or pre-parsing that XML helps, and that's what we'll see in some of the benchmarks. So the two things compared with ELT on the left, which is load as is and then transform on query, it's very flexible because during the query time we can pick and choose what we want to and how we want to transform data, versus the ETL side, it's geared for performance. Now, the simpler the format, obviously ELT is well suited, but with XML, what that means is that for every query, we'd have to parse that XML over and over again. So the two approaches can kind of be symbolized here this way. So on the left, you have more of a on-demand parsing, which is the ELT form. And then if we take those XML files, pre-parse them, and materialize it in some format, then we can access that data without having to parse that. Now, what does that help us with? Well, two things. One is all the tags can be removed, and that helps us in storage. And then in processing time, we spend much less CPU. So just showing that on the left, we take the raw XML and parse it, use it through Hive, Pig, or MapReduce. And by writing Pig UDFs, user-defined functions, we can apply the parsing on the fly. Now, this is suited, as we'll see later, for experimentation purposes. Like if you want to see what value is there in the XML, can I do something with it? What fields I need to take to do some analysis? Then we'll see that this is a good approach. Whereas once we have tried out certain queries and we see that there's some value in it and we want to productionize that analysis, then we could take the raw XML, parse it out, write it into a suitable format, and then perform operations on it. So this is more suitable for production workloads in which queries are more established, something that may have to be run every hour or every day. Then this is a much suitable approach. Now then the question is, well, what format do we materialize XML in? And XML being nested and can have arbitrary nesting, we need to have a format that will allow us to define a similar structure. We could flatten the whole thing out, but then that's going to result in several nested elements being flattened, and that'll result in duplication of data. Versus Avro is one format that is built for a Hadoop type environment in which we can have arbitrary nesting. So we could have records and arrays of records. Records can contain arrays or records and so on. So it seems like a perfect candidate. Plus, it was defined for other reasons as well. It is, if you look at the last bullet there, it's splittable. So the Avro file that will be written out after parsing can be split and run across multiple mappers. The other advantage here, the metadata is stored at a file level rather than in each record. So unlike XML, where the metadata is stored along with the data, whereas in Avro, you have the metadata, or rather the structure defined at the file level. All the records in that file go with that schema. So it is more suited for batch type processing, where we have to do analytics on it. As far as the Avro API is concerned, very simple. There are generic objects. It's in fact called generic record and a generic array. You could have a simple like a get field, a put, and that will construct your Avro tree. Very simple, and it has interfaces in other languages as well. So we'll take a specific use case and then we'll go through it. So the one that I've taken is XML, which is the Financial Information Exchange. So there's an XML database benchmark which provides data generation for XML type messages. And they have some canned data as well as a data generator. So we use that for this case. A simple, very simple entity, kind of customer orders. And so right now we're just going to look at orders, meaning these are orders of securities like stocks or mutual funds, bonds, etc. that will be traded. So every message is an order, or every XML element will be an order, which has multiple nesting inside it to have other fields like quantity, and we'll see some other structure here. So as far as the mapping goes, from the XML, what we did was, it's a pretty straightforward. Elements with nested, repeated elements are more like lists, or in Avro terminology, it's an array. And coinciding that with Pig, it's more of a bag. So ultimately, you end up with bags of tuples. Each tuple is nothing but a record in Avro. And hence, from XML, any element which has attributes and probably simple elements like text elements will qualify as a record. So we take that record, map it to an Avro record, which will be mapped to Pig as a tuple. Now for Hive, Hive can use a Avro schema as is. So I'll show in a bit how you can define a Hive table on an Avro data file. So this one may be a little hard to read from there, but just to give an example of an Avro schema, basically it defines something like a record which has fields. So you have all the fields in it, and a field can also be a record which can have its own fields, and it can go on, so forth. So basically an Avro structure can be defined arbitrary depth. So what we're taking is, we're taking the XML data, mapping it into Avro so that we can strip out all the tags, pre-parse it, write it into the Avro structure, and then materialize it. Then when we go back in and read that data, there's no more parsing to be done. We just, when we read off of the Avro file, we get a Avro record to process, and then we can traverse through a record and say, get this element, and then get this record, get this, and so on. So it makes processing very faster, very nimble. So a corresponding pick tuple will look very similar in terms of a record being mapped to a tuple, and then an array being mapped to a bag. You can have arbitrary nesting here as well. So for Hive, we have a serializer deserializer, which is generally called a SERD, that's available to read an Avro file, which we can provide the schema for. So once we have an Avro schema that I showed you in the previous slide, then Hive will take it as is and map it into its structure. So now you can write Hive queries on the Avro data as is. So you could say select whatever fields you want to select from that Avro structure, and if you want to traverse into arrays, then you can do an explode on the array, which will kind of flatten it out, and then you can traverse through the elements in the array. So from Avro, we can access the data through Pig, through Hive, and through MapReduce. It's the same format we have, Avro input format. And once we use that, we get an Avro record, which is a generic record. You can get values from it, get the arrays, and then traverse through in a MapReduce code. So we took test data of 500,000 records and then just multiplied it so that we can have some volume numbers to run this test. So the first thing we wanted to find out was, well, how much are we saving in terms of storage? So just to give a overview of what we are doing, on the left we have the on-demand parsing, in which we take the XML and we parse it on the fly. So we have a simple pick query, which is just calculating the number of orders per account that has been done in the system. And we do that analysis through Pig and parsing the XML on the fly. So it's kind of like a streaming mode. We take XML documents, parse it, take the values. Nothing is materialized there. We do whatever our grouping, and then we spit out the output. Whereas in the other comparison is to take the XML files and then pre-parse it into the Avro structure, and then using the Avro files to access through Pig or Hive, and then do a comparison between the two. We wanted to see, one, storage-wise, how much are we saving by taking it into Avro, and then processing-wise, how fast we do it, and what kind of resource usage is happening. So the base data, if we take, this is just a sample file. In fact, I'll probably show a much more visual representation of that same thing. So you have the uncompressed XML, so a sample of say 750 MB. That's the uncompressed XML as is that we've taken. And if we just do a gzip compress on that same XML file, that reduces it at least by about 6 times or 6 or 7 times to a size, obviously because of the tags being repeated. And this may depend on the type of XML. If your XML is 2 verbose or has, in this case for FixML, they deliberately designed the XML schema to be as simple as possible. So they took, instead of having elements, text elements, they would just make it an attribute so that they can save on some of the tags, etc. So obviously, even with that, we're able to get a pretty good compression. Now, if we take that XML, rather convert it to Avro, and depends on whether we want to compress it by Snappy or gzip again. When we write out the Avro files, then we see that even further, we are able to reduce it by half. So ultimately, of course, the whole XML gets reduced into one of these. And Snappy obviously is much more elegant in a Hadoop environment, specifically because it's splittable, versus gzip, it's non-splittable. Regardless, generally for analysis, you tend to have a large volume of files, and hence you may still run out of mapper slots that are available. So whether it's splittable or not may not make that much of a difference, right? But I guess the general recommendation is to go with Snappy. So that's on the space comparison. So going into the actual performance, we have an environment in which we have a 18-node cluster, each with 12 cores and 48 GB RAM, 36 terabytes each with 12 spindles. So this is the sample query that I told that was written in Pig that just takes the Avro input and then the schema that was defined, which is a mapping from XML into the Pig schema. And we just do a simple extract or project the fields that we want, account and quantity, and then group by account. And for each of that group, we just generate the group and a sum, so a total of all the orders for that particular account, and then we just store the output. So this is a simple Pig script that was run both against the raw XML, in which case, of course, the UDF would parse the XML on the fly and then project the fields and then do the grouping. Whereas in Avro, there's no parsing, it's just straight load, and then, of course, the schema has to be given for Pig to know how the projections will be done in the processing. So the two approaches, hopefully that's clear by now. So we have a pre-parsed approach in which we take the XML into Avro and then we run analysis directly on the Avro versus parse on demand. So when we talk about the runtime, I would first just look at the lower portion of things here. So runtime in seconds, if we do analysis on the raw XML through Pig, in which parsing is involved, versus the analysis being done on parsed XML, which is the Avro format, right? You can see that the runtime is roughly, in fact, reduced by half in most cases. And of course, one of the cases, there's a blimp there maybe because of some system, some background jobs, or I'm not sure, we didn't dive into what happened there. But obviously, in most cases, you can see that it's at least reduced by half. So by going directly against pre-parsed XML, obviously the processing time is reduced. Now, in order to do this analysis on Avro, of course, we would have to first parse it and then write the Avro files. So this is the time it takes to do that process of loading the XML, parsing it, writing into Avro. Of course, clearly that takes a little bit longer than here, because here there's no materialization intermediate. We just parse it, take the values, analyze it, and then write it out. Versus here, we also materialize the Avro files, which is, as we saw earlier, was about 1/7 of that data. But still, it takes time, I/O, to get to be materialized. So which means every time we get a new file, we could be running this at the same time to take that XML, convert it into Avro. And once that is converted, that's a one-time job. So hopefully, all of your other queries should be able to leverage that pre-parsed XML. So how many ever times you run, then that much benefit you get. Versus if you hadn't done the materialization, then obviously it'll be every time we do the query, there's parsing that happens. Now, this is just one side of things in which we compare the runtime, but there are much more involved. So from a CPU usage, so this is just looking at a couple of things. One is the user time the CPU spends and the system time. So clearly, if you look at it, the analysis on raw XML versus on the Avro or the pre-parsed XML is again roughly reduced by half. So rather, say supposing if we use 30% of CPU, then really we're using about 15% of CPU, which means during that time, obviously, we can schedule other jobs. So the more we conserve on resources, obviously, the better it's going to be. And then comparing the memory usage, so every XML loaded in and then parsed through recursive descent, and versus in Avro, we just retrieve the structure is already defined, and we just access the fields, so it does an index, versus in XML, it has to go through each and every element in order to get to whatever the data we need. Of course, this may depend on the type of parsers we use. So in this case, we did use DOM, which was easier. Not just easier, but also we could traverse through going back on the tree and coming back. So there was obvious benefit, but from a runtime perspective, maybe a SAX or a STAX might be faster and maybe lesser on memory. So that's one caveat I just wanted to mention that. So as far as the results goes, once we have a pre-parsed output, then roughly the runtime is going to be reduced by half, and this is for every time we run the query. So obviously, this is well suited for those cases when we have a production type queries that we have canned already, we have implemented, and we just run it over and over every day or every hour, then that will benefit from this approach. But obviously, which means we need to make sure that we parse out everything from that XML into Avro. So if for some reason we take only a few fields and materialize it, and if we throw the XML, then we might lose some data which might be of some help eventually. So the more complete we are in the process, obviously, the more better it'll be. Versus doing the on-demand parsing has its own advantages, obviously. So if queries are more experimental in nature, if you're just trying to find, well, what value do I have in the XML, or if I'm not sure what fields I'm going to take, then a on-demand parsing might be a much elegant approach, because we're just doing it on the fly, do a query, and check the results, and we are done. There's no materialization being done, because one thing to note about materialization is that the moment we write something out, it's become stale, in the sense that in order to go back and pull some other fields, you'd have to do that reparsing again. So it'll be good if we can take everything from the XML and move it to Avro. Then obviously that's the safest alternative. So it depends on how your usage is. So some of the caveats, like one of the things I did mention in this case, not all the fields were extracted, because obviously there were some optional elements, but we think we got like at least 90% of it to make sure we have a good comparison. Then the other thing is also about keeping up with versions. So if XML version changes, if they put out a new XML version, then obviously we'd have to catch up with that in the mapping. Versus if it's an on-demand parsing, then we can account for that in the parsing, in the analysis code. So also the numbers may depend on the type of data that you use and the mapping that is being used. So let me talk briefly about some of the other alternatives that we have. So mainly in the form of columnar storage. So that's in fact coming more and more up to light with some of the newer changes that have been done from a RC file. So just for those who are not clear, it's a record columnar format in which the columns are stored separately along with row groups. So that way we could have much more column compression. And also, I think there's one slide to talk about that. So some of the benefits of going with a columnar approach is that it's still going to be a MapReduce candidate, because all we are doing is we are separating the rows into blocks, and then within the block, obviously, it's stored by column. So if we do a column projection, so out of 100 fields, all we are cared about is 2 fields. In the Avro, what we are doing is we are pulling the whole Avro record into memory, and we are then accessing the fields and then, and then throwing it away. Versus if we would use column compression, then only the fields that are being projected are retrieved from disk. So you can save tremendously on I/O, which means your runtime is going to be pretty fast. The third thing is that columns generally have much more repetition, especially if they are values that are having some kind of enumeration, like say some things about if you have a few values per column, then obviously storing it in column format can save you on space, because now you're just sort of saving one value instead of repeated values being saved. So in fact, this is the same type you'll see in some of the NoSQL types that are there. Some of the analytics engines like Vertica, they do columnar storage. So other types that are interesting, of course, this ORC is an optimized record columnar format, and that's something new. It hasn't been released. It's, I think they are targeting for this year. It also has certain indexes built into it. So for certain values, they know exactly which row to go to, rather which row to skip. So it'll further reduce on the I/O churn. Instead of retrieving all the rows, they should be able to skip through certain rows which may not match the condition. So those two are very good candidates. The third is Trevny, which is a sub-project within Avro. That also supports a columnar format, in which the Avro format will be columnarized, and hence you won't be retrieving the whole Avro, and rather projecting out the fields from it. So that's another interesting candidate that we're going to do some more benchmarks on. Parquet is another one that is being pushed recently, and that's another interesting format that can support Avro as well. So in summary, what we are trying to look at is we have XML data, which is large and complex. Whether we want to do parsing on the fly per query, or we rather, if we pre-parse it once and then move it into some format, either Avro or a columnar format, then our queries will be much more faster, no parsing again to be done. But obviously the trade-off is in flexibility. If you want to change the format, or if you have not retrieved all the data in the XML, then obviously parsing on demand will probably be better. And just a final note on which approach to take. Obviously, if it's more of an experimental role, then don't do materialization. Rather, go against XML, try to look for value. Once it is established, then move it as a candidate for materialization, and then run queries on it. That's about it. So we have time for questions. Please come out to the mic so that others can hear.
So for the raw XML, how are input split? So let's assume you've got an XML which is heavily nested and very large, so maybe a couple gigabytes and so forth. How are input splits calculated when you're dealing with very nested structures and it's in raw form? And do you have the same problem with it when you convert it to Avro as well?
Right. So how are the input splits are going to be identified? So one of two things. Either we can store the XML as a gzip file. So XML in its entirety stored as gzip, and knowing that gzip is non-splittable, when you run your mapper, you'll be guaranteed to take the whole XML as is and do processing. Of course, that's a naive way. The other way is to have an input format that will recognize the XML start and end point, and then take those additional elements in or throwing it away, so that you have one complete XML. And actually, Mahout has that XML input format that will take out XML data given a tag. So you can give a tag, and it'll do pull your XMLs as logical blocks. So even though the block split may happen in between an XML, rather the XML input format will give you a complete XML at a time.
And in your benchmarks, did you use a?
Yeah, we used a gzip.
So you didn't use the parallel compute. You just had essentially one mapper
right,
that got spun
per file. And now that's the one thing I did mention earlier. I'm not sure. Maybe it's good for me to repeat it. So gzip is generally in a Hadoop environment, because of it not being splittable. They recommend Snappy or some other splittable format. But the moment you have, like, say, thousands of files, anyway, you can at most run maybe, depending on your cluster, of course. If you have 1,000 map slots, depending on your cluster size, then obviously 1,000 mappers will run at the same time for you to process all 1,000. But say if you have only 250 slots, whether it's splittable or not may not help you in that case, because you can only process 250 files at a time. So even if it were splittable, still the rest of the mappers, even if it was like, say, 1,000, they still have to wait for these to complete.
What I've typically seen is people actually flatten out the XML structure to be able to split it more easily. Did you guys consider that approach?
Yeah, so flattening, that is definitely one of the, so if you look at the RC format, that is more of a flat kind. So we would have to take the XML structure and make it flatter and store it in RC, or rather the ORC, which will come out later. So it being in columnar, plus it having some of the optimization of indexing in the ORC will definitely help in that case. So that's certainly an approach to look at. Versus just the downside to that is when you flatten it, then it's more of a relational format. So for some type of queries which may have to do at a record level, so for example, if you have an order which has multiple items, and your query is such that you want to look at the number of items per order, then in a relational approach or in a flattened approach, the first thing you have to do is group by an order ID.
Sure.
Versus here, when you take an order, you know that you have all the elements in there as an array in the Avro format. So that's the one advantage. So there's always certain queries that may be more suitable in an Avro versus some queries may be more suited in a columnar, very flat approach. So that's why the Treveny and Parquet are more of operating on the Avro format and then being able to do a columnar on the Avro format itself.
Sure.
So if we are not going to look at some nested object, then that object will not be retrieved at all.
Okay.
Versus we'll just do the projections on the fields that we want. So maybe that's the way to go.
And one last question, by converting it to Avro, do you get around the problem of splittability? Does materializing into an Avro format then allows you to split that materialized view? So
Yes,
that's one, okay.
it is splittable, yeah.
Yeah, thanks.
Thank you.
When you were speaking in respect to flattening, you're not actually going to the same extent, say you had a nested structure like 3 levels deep, say 3 arrays deep. And like in a Hive, you could basically do like
Explode.
3 lateral views, lateral view, lateral view, lateral view, which probably doesn't perform at a certain level of depth as well as something else, but you're not considering flattening to that extent, right?
Well,
Such that your possible flattened input structure would be the same as the fully denormalized structure that multiple levels of lateral views could give you, right?
Right. So if we want to store it in an RC file format, then obviously you're talking about that level of flattening in which we have to do a lateral explode and then make it more relational. But Treveny or Parquet, I understand, will be able to handle that level, keeping those levels of nesting in place without having to flatten them. So that'll probably be a better alternative.
At a certain level, like maybe even past 3 levels maybe.
Or more, yeah. Okay. And certain types of queries may help using in that format rather than relational. So you would have to choose between one or the other.
Yeah, I mean, if you're doing like lateral view, lateral view, lateral view, the query itself gets pretty complex at that point.
Very nicely, yeah. Any other questions? All right, thank you very much for listening.